Morning, everyone. I'm sorry for the delay, for the technical issues. Let's get started. Okay, welcome everyone to the GAZE 2023 workshop. So this is already the 5th workshop we have. So the very first our GAZE workshop started in 2019 at ICCB 2019. And since then, we have been organizing GAZE research workshops, ECCB and Cvpr, and now it's the 5th. So we give a big welcome to all the attendees from the organizers. So we have sponsors and organizers, sponsors from University of Birmingham and TU Delft and ETH Zurich and the NVIDIA and Google. So this workshop could be possible thanks to these very valuable program chairs' help. They helped us reviewing the submitted papers to the workshop. Also, we have excellent workshop sponsors who started from the very beginning of the workshop series. So especially NVIDIA sponsored us with some GPU card for our best paper award prize. And Google has been sponsoring us for the best poster award. And Toby, generously, they've been sponsored us providing for the workshop papers for eye tracker. So this year workshop, we have 2 invited keynote talks, and we have 5 peer-reviewed workshop papers will be presented out of 10 paper submissions. And also we have 5 invited poster presentations from Cvpr 2023. Today, we have 2 invited keynote speakers, Errol Wood and Ruth Rosenholz, which is going to follow after this opening session. And the best poster award, this is important, so will be voted by audiences during the poster session. And the most voted poster will be awarded after the session. And the prize will be sponsored by Google. Thanks, Google. And all workshop papers will receive an eye tracker as a gift from Toby. So we hope this will be very much helpful for your eye gaze research. So this is a workshop schedule for today. So after this opening remarks, talk will be given by Errol Wood and then Ruth Rosenholz. And also we invited poster spotlight talk will be given by each of the author from Cvpr papers. And then we will have coffee break with poster presentation. And the poster presentation venue will be downstairs on West Hall A. And you can check your poster number on our webpage. And then the workshop paper presentation will be followed. And then we will conclude our workshop afterwards. So hope you enjoy today's GAZE workshop and hope you have a good time with us. Okay, so let's move on to the invite keynote speaker. So today we're going to start with Errol Wood. So Errol is a staff software engineer working at Google AR/VR on digital humans. He got his PhD from University of Cambridge and working on the gaze estimation. And after that, he joined Microsoft MR/AR lab in Cambridge. Now he's working at Google. Okay, let's welcome speaker. That's did we use this side or the other side?
Oh,
All right. Just never works when you want it to.
Let's hope it doesn't disappear as quickly as it. And then Zoom as well.
Yes.
And that's the last one.
That should be the last bit. Probably. Is it possible also for you to turn? That's okay.
Let's not add to the.
Okay, all right.
Thing. Yeah, let's
Okay.
to make it easy to this point.
Yeah,
Is that it's really a dynamic angle anyway.
yeah, I believe so.
Very
Yeah.
powerful.
It's your better side. Yeah.
Okay.
Okay. I think we're ready to go.
Cool. All right. Really, thank you for a very nice introduction, and thank you all for coming today on Sunday morning, 8:30 a.m. Maybe you guys are as jet lagged as I am, and this hasn't been so painful, but I'm extremely grateful that you all came along to listen. So yes, I've been working in a kind of augmented and virtual reality devices for some time. I spent 5 years at Microsoft, where I spent a lot of happy times working HoloLens 2, holoportation, face tracking. And 1 year ago, I moved to Tavo Bila's team in Google, where we're working on all sorts of digital human things for augmented reality and virtual reality, including synthetic data. So this is a story that starts and ends with gaze estimation. So you heard, I did gaze estimation in my PhD, and it's going to take a few detours on the way. And when we think about synthetic data, it's nowadays, I think, with all this amazing progress with machine model architectures, the biggest problem you have isn't choosing the right model, is actually finding the right data. And you can label that data, but you can also render data using computer graphics, and that's what synthetic data is. So I find this is a really interesting time to talk about synthetic data. So over the last few years, I think we're starting to see a bit of a paradigm shift. I remember the last big conference I went to before COVID. So that was ICCV 2019 in Korea, which was an amazing location. That was really great. And there, during a workshop on hand tracking, I saw this slide, and it said something like, synthetic data does not equal real data. And the presenter said, everyone knows synthetic data isn't as good as real data. You could never get something to work that well with just synthetic data alone. And this was not a controversial statement. So the whole audience nodded their heads and were like, oh yes, that's true, that's true. And there's always issues with the domain gap, and performance and training with only synthetic will never work. So I was sitting in the audience, just like you guys are today, bemused a little bit, because at that conference, for the first time, we were demonstrating HoloLens 2, including this hand tracker that I've been working really hard on. And it wasn't public at the time, but this had been trained using synthetic data only. And although bemused, I also empathized with the presenter, because making good synthetic data is really hard. It requires skill sets quite different to those of a typical computer vision researcher or software engineer. And although, at Microsoft, we managed to ship several products already with synthetic data like Connect and HoloLens V1 and HoloLens V2, we're still writing the cookbook, so to speak. What recipes work well and what recipes don't, which are dead ends. So in this talk, I'm going to share with you some of my favorite synthetic data recipes, starting with synthetic data for gaze estimation in my PhD, which I worked on a long time with Tadas, who I'm very glad has joined us in the audience. And then moving on to hand tracking for HoloLens 2 and a bit of body tracking and face tracking, where finally, again, as we do face tracking, synthetic data will help us tell where someone's looking. And in each story, I'll highlight some key lessons that I learned, all of which helped me develop, I think, kind of best practices for how to make synthetic data and how best to use it in production. So when I started my PhD in 2013, so I'm not sure, which of you guys were in the field at the time. Deep learning, right, was revolutionizing computer vision. It was changing everything, and every field wanted a piece of the deep learning pie. And it was clear that these deep learning models were more data hungry than those that came beforehand. And some PhD students were, very motivated and very eager, like Zukong, and organized massive data collection efforts to feed this deep learning beast. But I was lazier. This sounded like, way too much work. Instead, I was aware of a then recent work about the Microsoft Connect, where synthetic data was used to train a body tracker. And since I had, some ability with 3D modeling, I thought, maybe we could do this for gaze estimation as well. That'd be interesting. So the authors of the Connect paper realized that several key factors were important in making synthetic data work: realism, diversity, and controllability. And these factors will keep popping up, throughout each of the stories we hear about today. So the synthetic images must be realistic enough to cross the domain gap. They must be diverse enough to generalize to the real world. And finally, the system that you create should be controllable, so you can actually make the data you need. Connect was trained on depth maps only, and we need color images for gaze estimation. We want to bring, like eye tracking to the masses, right? With just like a webcam, that's kind of the dream. So the idea is we need to render color images of eyes, and rendering realistic depth maps is one thing, because there's maybe much less of a domain gap to cross, but realistic color images of human faces are much harder. In fact, this is the holy grail of CGI for a very long time. So, I said I had some rudimentary ability for 3D modeling, but modeling realistic human heads was way beyond like what I could accomplish. But luckily, at around the same time, early 2010s, photogrammetry, I think, experienced a step function improvement, probably because of a combination of, more affordable, really good digital cameras. So you can get people that have 40 or 50 of these high resolution, very sharp focus cameras, and better photogrammetry software like Agisoft. And the result are scans like these, really high quality, sub-millimeter level accurate 3D face scans. And this is great because you can just buy these. You don't need to be really good at 3D modeling to use them. And they are somewhat diverse. At the time, you could maybe buy about 10 of them, and you get a reasonable spread of diversity. So the main issue is that these weren't controllable. So these scans capture a single instance in time very accurately, but for us interested in eyes, the eyelids have to follow the eyeballs as the eyes move around. So I retopologized each of these scans and rigged it up with blend shapes, like a very traditional computer graphics thing, so we could animate the eyelid following the eyeball. And this is what it ends up looking like, which was not bad. And you can see how the eyelid unfolds and so on. And we got some kind of interesting results using this that were kind of interesting for the time. So the main issues is that it took, like a day or so to render all this data on a single machine with a GPU. And we're not actually talking about very much data, only 10,000 images, which is probably considered quite minute for a modern deep learning data set. And like the more data is better, right? Like, how do we get more than this? We don't really want to be rendering for days and days and days. And secondly, with diversity, so we had 10 of these head scans. There's a lot more than 10 people in the world, and they look different. Like, how can we make more people? So the next thing I focused on was, addressing these two problems. So the first one regarding rendering, that seemed quite straightforward. Like the bottleneck is this amazing ray tracing renderer we have that makes these quite realistic looking images of skin with subsurface scattering, and that's nice. But it is a bottleneck, so we could replace it with Unity, which is a pretty reasonable tool to get started with and render hundreds of images every second. So that solves the scale issue. And diversity was a bit more interesting. So we only had 10 of these head scans, and nowadays it's possible to purchase hundreds of these sorts of scans, but at the time only a few were available. And indeed, we're on a PhD budget, so purchasing hundreds of head scans might not be so amenable. So we figured, wouldn't it be nice if we could pad out the diversity a bit by blending between these subjects? So we did this by creating this 3D morphable face model just of this eye region. So there were lots of previous models for the whole face, very successful, well-used face models, but none really had the kind of fidelity we wanted around the eye region, and none had this separate movable eyeball. So we made a new one, and this was done by bringing all these scans into correspondence and building this kind of traditional generative model. And equipped with Unity and this morphable eye region model, it's possible to render a lot of data. So you just let this thing run, and we rendered like over 1 million images, which is pretty sizable, I'd say. And what you can do is when you have so many images, you can kind of do something like just nearest neighbor match. So you have an input image, and you say, I've got my enormous database of images. What is the nearest synthetic image? And the top rows, you can see the real images, and the bottom row is just the closest synthetic images that matched. I think it's pretty interesting. You can see how you can estimate gaze for input eye images where you probably wouldn't have any accurate ground truth otherwise. So the message of the paper was kind of different to maybe the reality, I think. So the message of the paper was like, more is better. It had like the word 1,000,000 in the title, right? Everyone likes more. You think like deep learning, more data is better. But there's this figure in it. And if you look at this dotted red line, which I think with dashed red line, I think we kind of made it dashed to kind of try to like hide it. We're like, no, it's the truth. And it's like, after kind of 10,000 images, the signal gets pretty noisy. It's like, is it really helping to have 1,000,000 images? Is 1,000,000 images better than 10,000 images here? I don't really know. And like, there are other things, like definitely you can like find closer matches just by rendering more images. But if you're thinking about just gaze estimation, I don't know if 1,000,000 images helped. And the message here is that infinite is not necessarily better. I think with synthetic data, you often hear this argument, which is like, with synthetics, you can make infinite data. And the kind of suggestion is that with infinite data, your problems will be solved. That's right, infinite is best. But another thing to think about is there are infinite numbers between 0 and 1, right? That's not like helpful. Like you can make infinite images, but if they don't cover the actual testing scenario that you care about, it's not that helpful. So we didn't have glasses or makeup, and so having 1,000,000 images wasn't gonna help there. So it's not just about the sheer number of images, it's also about or maybe more importantly than the number of images, are capturing the dimensions of diversity in your testing scenario or the real world. And I've never rendered a data set as big as this again for anything else. Like I think like 100,000 images is a really good number to get pretty good results with a lot of stuff. So following this, I did some kind of non-machine learning synthetic stuff for a while using model fitting, and that was the end of the PhD. And for those of you who have submitted a PhD, I'm sure you'll remember, after you've submitted it, you probably don't want to look at that topic ever again. You think like, I'm done with gaze estimation and eyes and eye tracking. And when I joined Microsoft after my PhD, someone asked on the eye tracking team, I was like, oh, are you interested in being involved in the eye tracker? I know you're familiar with eyes in any capacity, not like, I was just like, no, like just no more eyes. Like I'd gone to the point where I couldn't look at someone without thinking about like eye modeling or synthetics. Like looking at someone in the eye was just like, so I needed a break. And I thought hands were perfect, So eyes and hands are both parts of a human. But that's, I think, where the similarity ends. So eyes are kind of like a sphere, an eyeball's a sphere, and they rotate and are not that complicated in terms of shape. The hands, on the other hand, are highly articulate. So a single hand has as many joints as the rest of the human body. And they fold themselves over in weird ways, resulting in high self-occlusion. Eyes, on the other hand, have a lot of complex materials. They're, reflective and refractive, and they have all these tiny eyelashes, which get in the way. Hands are kind of much simpler. Hands are generally kind of naked. And also the HoloLens too, like in the infrared spectrum, hands can all look very similar. There's maybe a bit less appearance diversity in that regard. So, the topic itself is really cool, right? And especially with the recent Apple Vision Pro announcement, it's clear that other people as well also think hands are maybe the future of interaction. The way you can reach out and interact with digital things just like you would in the real world is a pretty cool thing. So at Microsoft, we had this good hand model fitter, but we needed to initialize and guide it. And so for that, we needed to do some more machine learning. Like in industry, there are well-established practices for getting a lot of real data labeled, of course. But even then, hands are very challenging because of the self-occlusions and stuff I described previously. So we decided to look at synthetic data, which Microsoft has a long history with. And during this project, we worked on a lot of different synthetic data pipeline. And actually, I think over the years, we ended up honing our philosophy around synthetics. And so this philosophy has two parts, like how to make the data and how to use the data. So how to make diverse, realistic, and controllable synthetic data. Scale is still important. We do want to render, a lot of images, maybe not 1,000,000. But we're not a fully fledged visual effects studio, as much as I, wish we had one of those with hundreds of artists. We need to do things procedurally. And this is where, parametric models come in, host databases, digital wardrobes, and renderers. So I'll go through them in turn. So enter the parametric model. So this is like the eye region model I showed you earlier. And these things work because luckily humans are all somewhat alike. It's possible to make a function that takes in a bunch of parameters and produces a human mesh or part of a human. And this makes it possible to create human parts procedurally and mix them up together, take one person's pose and replay it in another person's shape. And for hand tracking, we needed one of these model fitting anyway. And this hand model was built from a large collection of hand scans, and we made it look realistic. So it's not enough to generate, static hands, like big open hands. And another challenge is, how do hands move? And this is maybe less of a challenge for eyes, like, it's still, complicated, but, eyes rotate with pitch and yaw, and maybe the eyelid goes up and down. But something like a hand has a lot of degrees of freedom. And so we need to build this comprehensive and diverse pose database. And we capture a lot of these hand poses using a special markerless motion capture system, recording dense point clouds of hands in action, and then fit our hand model to them using this large offline fitting process. And the result is, thousands, tens of thousands of accurate hand poses. So another thing that, eyes have less of are clothes. People, wear glasses, but you get a lot of clothing that appears around the hands. And this is really important to model. This is harder to parameterize, so I don't actually encourage trying to parameterize clothing. I think people, try really hard to do this. But if you want really high fidelity, it's often just easier to kind of collect a large kind of database of high quality assets and sort of stick them onto your parametric model. So, sleeves, watches, rings, and so on. And finally, you need to render all the image. So this is what the result looks like. And this was the system we actually used to train the hand track on HoloLens 2. For those of you familiar with Blender, you might see the Suzanne monkey in the background. But this wasn't rendered with Blender. Actually, this was rendered with an in-house depth camera simulator. So the HoloLens 2 used a depth camera for hand tracking. And I think, nowadays people have realized you don't actually need a depth camera. But at the time, people thought you definitely did. And you can see it's these floating hands, and you get all these nice key point annotations and so on. And yeah, that was pretty useful. And, this worked quite well for us. So what was just as important as the data itself was figuring out how best to use that data. And this is something that, Andre Karpathy at Tesla calls the data engine. We call it the virtuous cycle, but it's kind of the same idea. So you want to improve both your synthetic data pipeline and your machine learning models. And this only happens once you've got testing in this loop. So you render your data, you train your models, you test on some real data, and then you use those discoveries from your testing to improve your synthetics. And things only get better once per cycle. So the time it takes to do this cycle is how often things will get better. So if it takes a long time, so let's say you render your data and it takes you a week, and then it takes you a week to train, and then, like 2 weeks later, you hand it off to your machine learning engineer, and they come back to you and they say, oh, I found some problems. And then you said, oh, no, you had a bug. And then it's like a long back and forth. So if this thing takes like a month, then your thing's only going to get better once per month. And that can be a problem. So what we realized at Microsoft, we needed to close this loop as tightly as possible. We needed to make it possible that, people could train, test, and, make changes to the synthetic pipeline in a matter of days, ideally. And that is generally possible if you can develop a system where the machine learning engineer is in control of the data they're creating. That reduces this kind of back and forth passing of things. So it's kind of, it sounds weird, but actually less communication is key. Like sometimes people think like, oh, people need to communicate more, but like the people best suited to solving a problem are those closest to the problem. So if you've got someone, going off to another team and saying, oh, I need this data, and then the data comes back and it's not right, and then they need to go back. This is a long kind of overhead that can really slow things down. So we call this, self-serve synthetic data. And like one example that worked quite well for us is that, or it can be different teams, but as long as they're working very closely together. So we had, so earlier I said hands all look the same in infrared, which is true, unless it turns out someone has tattoos. So tattoos like get very dark in infrared. And we shipped some models, and one of the nicest things about developing a product like HoloLens 2 is like when the products start rolling out, like off the factory line, and people start using them, stuff starts breaking, and they get back to you, they file the bugs. And that's, you get a really diverse set of, real test data. And one thing it turned out was that, if someone had tattoos all over the hand tracker just wasn't working at all. And so this was fine. And we went to our artists, and so we said we need some tattooed hands. Within a day they got some texture maps. We re-rendered it. Within a few days we retrained a model. Probably within like another few days, this model was shipped out in a fix. And that was a really great example of when this cycle is working well, things can go very smoothly. So after we shipped HoloLens 2, we're thinking about the next generation of hand tracking synthetics. And if you remember, we had these kind of floating arms, which was a compromise because we wanted to have super realistic hands, but maybe we didn't need the whole body. And this wasn't, fully satisfying because we use synthetic data to train the key point networks of the hands, but we use real data for the hand detector, which is like, finding a hand in a full image. So the next step was clearly going full body. And this is much more complicated than just a single floating hand by itself. We didn't have a parametric body model at Microsoft. And, I'm always a fan of buy rather than build, and amazing parametric body models exist in literature. So we licensed Simple for this. And, Simple has all these great pose databases and still has a very traditional formulation, very suitable for graphics tooling. So pose database is the next thing we need. And although there are lots of amazing pose databases for Simple, sometimes if you have a very specific thing in mind, like hand tracking, these pose databases might not be that suitable. Amass has lots of people dancing or fighting or swimming or running. And actually what we wanted were lots of people poking virtual buttons. And this turns out, even with 2 million frames worth of data, there's not much of this in Amass. So we built a mocap stage and recorded lots of these optical market data, and we use this algorithm Marsh to fit Simple into that. And then it's pretty cool, right? Because you can take one of these poses and replay it on different body shapes and get a really good diversity of data from that. So Simple is a great model of shape, but it's not realistic enough for making the training data we wanted. And one nice thing you can do is you can kind of cross this problem by using displacement maps. So we use the same source of scans that we used for the faces, these really high quality kind of millimeter level detail scans. We unwrapped them and applied them as texture maps. And as you can see, can look pretty reasonable. And we did something similar with clothing, inspired by some other work, Simple D, that uses the same idea to model clothing as displacements. And the result is something like this. So full body animation of hand tracking style poses, which we can then render from a head mounted camera. And that's really nice as well, because where the head is, you can also get a really good idea of where the head mounted cameras would be. And with a system like this, all of your training data can now be synthetic, which helps fast iteration and gives you new ways to prototype new devices as well. Yeah, so I'd always wanted to, following hands, I'd always wanted to return to eyes and faces. Eventually, I think part of me deep down realized I'd finally be ready. And when the opportunity came up, that was great. And yeah, something that often makes me chuckle is that people use this Unity Eyes tool thing that was released, and they find use out of it, which is great. And sometimes they email asking, it's like, oh, this is great. Like, how do I get the full face? I'm like, well, it's just a little eye. It's like, there's no face there, but it's reasonable for someone to think there might be like a checkbox to just give you the full face. But it's much harder to do, I think, the full face with hair, with clothing and everything. And this was something only possible, with a much bigger team. But again, even though much harder, same pattern, right? Be data-driven, base our work on parametric models, collect pose databases, use digital wardrobes, render it at scale. So parametric model-wise, we used a new one called MoEye. And this was, Flame is pretty good, but it didn't really have the fidelity we wanted around, especially the eyes, because we did want this thing to be, usable for eye tracking if we so desired. So we built this new one from really carefully cleaned up scans. And I think that extra level of care in the kind of scan preparation helped the model, look a bit more realistic enough for synthetics. And then we collected this expression database using a multi-camera capture studio. So kind of similarly to hands, we used, recorded over 100 people making various extreme expressions. And then we predicted dense key points and fit our model to those key points. And these, gave us around 70,000 sort of expression parameters we can use in our expression database. You can see some examples here. And for, digital wardrobe, so similar idea to before, but now we also have to care about the hair as well. So we built a large collection of static clothing items, accessories, and so on that we draped around the head, formal, informal clothes, kind of like athletic wear, leisure wear, glasses, masks, headphones, other head accessories. And this was like a massive effort to build up this collection over time. And this is nothing where it really helps to have this loop. So you'll train something and you'll know your training data is going to be perfect. Like you don't have any glasses, and that's kind of obvious. And then, you can add glasses, but sometimes it's maybe less obvious. Someone will say like, oh, I was wearing this giant face mask. And you're like, oh gosh, like, I guess I do have to add face masks to my training data. But again, because you can work with artists, we work with a lot of, we outsource a lot of this to good vendors we have a good relationship with, then you can get those added to your training data without too much friction. And finally, we render everything with Blender. So this is the the same renderer I used in my PhD as well, kind of evolved over time. So this is the photorealistic path tracer, and this gives us the realism we need and the ability to scale up without worrying about licensing issues. And so the result is these diverse and realistic faces with rich sources of label. And that's the kind of final factor I haven't talked about yet. This is the richness of label. So for a lot of the previous problems, it was just, you just need a few hand key points maybe. With faces, we started exploring much richer, more detailed kinds of label, like the dense key points you saw at the end. So a human might even be able to label hand key points reasonably accurately, though, or, with a face sparse 70 key points, they might be able to do that. There'll probably be some errors and noise, but with synthetics, these are perfect every time, right? You get them for free with your render. Obviously, it's still a lot of work to make them, but every time you render, you can get these really good labels. And so with these kinds of labels, you can do stuff like this. So you can train dense key point predictors. And I think here, finally, you can see, us coming back to, eye tracking again. You can predict these iris landmarks, and actually you can track where the eye is sitting in the face quite reasonably and where it's looking and what the eyelids are doing. This is also only made possible with some really good model fitting magic we have at Microsoft. So it's the same model being used for synthetics and model fitting makes a really kind of elegant system that is well suited for tuning and running in real time. Right. So, where are we going? So finally, onto what's next maybe. So that was the last project I worked on at Microsoft. So I just want to show some cool work that my colleagues did at Google. This wasn't myself, but I think it's fascinating how computer graphics is a field that's been around for decades, and I think many people think it's fully matured, and yet still in the last few years it's been totally revolutionized by this NeRF thing, and people are finding new ways to render images and generate them. And Jensen Huang said something like, soon every pixel will be rendered. No. Soon every pixel will not be rendered, it will be generated. And I'm starting to believe that. And I think things like, NeRF and these generative image models will, people are already using them together. And, we've got to figure out how to, keep using them for generating really realistic face images as well. And something like the eye is very challenging for that, right? Like NeRF by itself doesn't model refraction and reflection, but at Google, we have these light stages, and we can record really accurate one light at a time kind of data and do some model fitting, and then we can build these special kinds of NeRF that do separate the eyeball from the skin, and get really cool results like this, which I think is pretty impressive. And yeah, as I mentioned earlier, it's really hard to make good synthetic content. It takes a lot of effort, and I think things like stable diffusion will help make that easier, I hope, or more. You'll make it easier to add controllability and diversity to your data sets, perhaps. And finally, I'd like to show off some of the work we've been doing at Google in our team. So here are some of the faces we've been collecting. So we have a large data collection effort at Google to really try to understand how faces move, what they look like, to really try to model the diversity of the human population in all its regards. And so here you can see some face registrations where we capture the lip motion, and there's no sliding over the skin. And this is the sort of source data which we can use to make new generations of synthetics that achieve like a really high degree of detail and fidelity, like some of the stuff you see here. Yeah, I'll just let this one little performance question there. Right. So to end, I think, there are kind of two lessons I want to, go back to, and that's this, I've been repeating this kind of pattern over and over again, right? So this is one pattern that's worked quite well. And there's many different ways of using synthetic data, like many people use these kind of static scans very successfully, like for PyFu. But for many of the problems I've worked on, this is a pattern that's worked well. Starting with a parametric model, building a post database, building a digital wardrobe, and rendering it all procedurally at scale. That's how to make the data. And then maybe more important is how to use it. And it's one thing, if you can make the data, that's okay. But if it's not being used, if it's not useful for someone, that's not great, right? And so with that, it's this data engine or virtuous cycle that's incredibly important. That's this, you must make sure this loop has as little friction as possible between rendering, training, testing, testing on real data always, by the way, like if you want to get useful insights, and then tuning or improving your synthetics. And once this cycle becomes really, really smooth, you can iterate very fast and accomplish some really cool things. So yeah, thank you very much.
Okay. Thank you for the talk. Any question?
Yeah, for some of the big synthetic models, where you explicitly modeling the eyelash geometry, I know a lot of approaches use like custom-created for a lot of that takes on that.
Yeah, I think we model eyelashes in a variety of different ways. I think in real time we model them with cards because it's like we wanted it to be rendered faster. But I think it's useful actually. I moved away from real-time renderers, maybe partly because as I moved into the industry, it was. We had different tooling, like with the HoloLens 2, we had a very custom renderer. So, and when you're rendering offline, you can use strand-based geometry. And I think it adds a lot of realism, especially for super close-up renders. Like when your camera's really close to the eye, you do want the strand-based geometry to model how light scatters through it. Like if you have some lights very close to the eye as well, you kind of want that light bouncing around inside the eyebrows to cross the domain gap. Yeah.
Like if we use this parametric type model, so there are several hyperparameters based on the person to person. How do you handle those kind of like body size, hand size, something?
Yeah. So the good thing with parametric models is it lets you be data driven, and this is a key difference to an alternative might be you say, oh, go to TurboSquid and find some hand models and get the technical artist to try and animate them. But I'm not a fan of that approach because it doesn't let you be data driven the way you can be with parametric models. In general, I kind of just like to replay sometimes it's if you can just replay an actual performance, like this is someone's face geometry with we're not mixing kind of poses and shapes, but I mean other times you can do that. You have to worry about things like if you change someone's body shape and they're doing some if they're touching their hands like this, then if their arm gets twice as long, you might get some issues. But I mean, it's very case by case. I think you have to figure out what you can get away with as you're adding diversity. But as you collect more and more data, you might not even need to mix it around that much. Like if you can capture a lot of data, you maybe just can replay it and get your perfect labels, and that is good enough. Or maybe slightly perturb it, change the neck angles just a bit to get some diversity. I think it's very it takes a lot of like judgment to tune these systems, unfortunately still. but all, as you say, there's a lot of levers. All the levers are there, and if you can get into a situation where it's quick for you to render and then look at your results and then maybe train with them, you can do some kind of small sweeps to see what works best. Okay, sorry.
So I wanted to ask a question about the light falls on the eye as well as on different parts of the body. How do you model like different light environments? For example, if it's a very light environment versus a darker or more light environment?
Yeah, so for faces in particular, we kind of, I mean, for images like this, which are a bit further away, we use high dynamic range environment maps, which are really easy, it turns out, to get online. There's great sources with permissive licenses, and they model strong light very well. And how an eye actually looks in that lighting environment is, that's a good question. So we try our best to model the materials quite accurately. With something like iNerf, this is all, this has come from the actual capture light stage itself. So we have this one light at a time system where it'll fire a lot of different lights, and you can then do a lot of math and figure out how this surface reacts to lights from different directions. But otherwise, it's more sort of traditional CGI of trying to say, well, I know the iris is this refractive index, and we roughly know the skin behaves in this way with subsurface materials. So a lot of it is maybe more artist-based, and that's not something we should shy away from necessarily. I think as scientists, we're very tempted to be really data-driven the whole time. And I just answered another question saying it's important to be data-driven, but also I think balance is important. It's also important to realize that sometimes the right call is to kind of just eyeball it, like pardon the pun, and just say like, okay, this looks realistic enough. Because artists have been doing that for thousands of years, right? It's like I know Michelangelo didn't. Well, maybe he did, but I think probably there was a lot more eyeballing and just kind of art going on than collecting. Yeah, it's this overloaded term a lot.
So there's a fair amount of evidence that when a human estimates another human's gaze direction, that they're mostly using the eye area just to get gaze direction relative to the head, and then they're using the head to get a more absolute direction. So I'm curious what you see when you add do you have a sense yet of when you add the head to your data, what happens with the eye gaze estimation?
Yeah, good question. I think it is important to treat the head as a whole when you can. And I think we've seen that in the field as well. More and more approaches are just doing just that, because you get a lot more information from the whole thing. And I think at the beginning, also maybe because of the tools available to us at the time, people were just focusing on these small eye regions. But when you get the whole head, and I think we see this a lot with the kind of model fitting stuff, it really helps just seat the eyeball in the right place, because sometimes from just a small image, you don't know where the eyeball is, like half a centimeter up or down. But if you get the whole kind of face, you can then get a better estimate for that. Especially also if they look around during a sequence, you can kind of optimize for that as well, and that will help I think get a better eye gaze.
Okay, the last question, sorry.
Have you ever noticed any need for the main adaptation?
Good question. I think we do domain adaptation, but maybe not in the way that is often seen in the field. Like, so all of our images that we render are, people would say like, generally, come on, get over there. Like, oh, they're too perfect. This is a common argument. It's like, synthetic data never works because the images are too perfect and they're not like a real world image. And that's why you must mix real data in. The most success I've ever had is never mixing in real data and not actually using these kind of machine learning forms of domain adaptation. But of course, we do a lot of appearance augmentation at training time. So like a very, very aggressive augmentation strategy is used. Loads of, the standard stuff like hue, contrast, JPEG, blurry, motion blur, noise, grayscale, I don't know, like, all that stuff. And that is a form of domain adaptation in itself. And that's how we go from these, perfectly crisp, perfectly color balanced images to the sort of like awful images you get in the real world. But I've not used a learning-based method for that, mainly because, well, two things. One, that I'm worried that it will change the semantics of the image too much. Like it'll move around an eyelid by a few pixels. And actually one of the main strengths of computer vision, of synthetic data, is its perfect labels for training models. And if it changes the semantics, that's an issue. And secondly, I think because it's a distraction. If you might think, okay, it's not working, what do I need to do? I could improve the synthetic data, or I could try to train some domain adaptation thing. And I think the best investment is in just improving your synthetic data. Like you can render photorealistic images with good diversity, and that's what you should focus on. And as a team, you've got a set amount of resources. And if you try to do domain adaptation, I think it's less valuable, and it then doesn't generalize to a new project. Let's say now you've got a new camera or a new device, all your domain adaptation maybe is no longer that useful. So that's why I've kind of always pushed for a different approach.
Okay, thank you. Let's
Thank you guys very much
for the Okay, let's move on to the next talk. Oh. Okay, the next talk will be given by Ruth Rosenholz. Ruth studied and got PhD from UC Berkeley, and she worked at the Palo Alto Research Center. And then she joined MIT Department of Brain and Cognitive Science, and she's a principal research scientist in MIT now. And today, Ruth is going to give a talk entitled Human Vision at a Glance.
All right, are we good? The slides are on Zoom, everything's good? Okay, so hi, thanks everyone. It's delightful to be here. I'm very excited to be invited here. My training is in computer vision, and this used to be my conference, and but for many years now, instead, I've been doing human vision, both basic science and also I'm interested in applications of human vision to all sorts of things. So, but anyway, it's nice to be back. Nice to have an opportunity to be back at my old conference. And these days, hold on, let me just get to where I can see my stuff without seeing Zoom. There we go. These days I study all sorts of kinds of human vision, but these days a lot for the last decade and a half, roughly, a lot of it is about peripheral vision and attention as kind of the main topics of interest. And so this is going to be a very different topic for you for the rest of the session. It's sort of about the places where your interests and my interests intersect, I think. And that basically is, once you know where someone was fixating, what they were looking at, what they're pointing their eyes at, then what? What can we say based on that about what information the observer has processed, what they've noticed, what their situation awareness is, like what they know about the scene. And another question that sort of started me being invited here is, suppose my eye tracking isn't that good. What can I say about what a person will know? So for instance, just as an example, if your fixation is at that X on that sheep that's to the right, then the question to some extent is, are you processing the sheep, and that's mostly what you know about? Is it possible you're also processing the dog and the grass, and you know more about the scene, and so on? And as you can tell, probably just from pointing your eyes at the sheep, you do see rather a lot about the rest of the scene, even though you're only pointing your eyes at the sheep. And that, in fact, is consistent. But we know that people can process more than just where they're pointing their eyes. And here's a demonstration of that. Again, if you fixate on that plus there, I'm going to show you a scene very quickly and just see what you can see while fixating there. And even in that brief presentation, you probably saw that there is a woman and a child. Maybe they're in kind of a school environment, right? They're playing some sort of clapping game, or maybe they're high-fiving or something like that. That's what the image looks like, so you can compare with what your impression was. And it probably even seemed pretty natural to get that information across the field of view, except, for the short presentation that I flashed the image at you, it probably seemed pretty natural, right? And so once you realize that people could be perceiving information across the field of view at a given fixation, you want to know what information could they possibly be perceiving given that fixation. And for that, you need to know about peripheral vision. And so just some terminology here. If you hold your hand up at arm's length, your thumbnail is about the size of your fovea, your rod-free fovea. The rest of it is what I'm calling peripheral vision. And you probably have heard a lot of myths about peripheral vision. And so I want to start by dispelling some of those myths. You frequently online, for instance, see this claim that peripheral vision has terrible resolution. There's virtually no color vision, that it's all but useless. It just serves to guide the high resolution fovea to the interesting bits. And maybe even with an image like this that attempts to show you what information is available across the field of view. And certainly there's some truth to this, the terrible resolution and the no color vision, but it's been greatly, greatly exaggerated. And I don't want to get too far into the weeds here, but I think it can be worth explaining why it is that people have this misconception so that you can be aware of it. So as you probably know, the eyes have two kinds of photoreceptors, the rods and the cones. The cones are the ones that are dominant in daylight vision, and they fill the fovea, they support color discrimination. And so for most tasks, if you're in a well-lit environment or it's daytime, you're talking about the cones. And so you've probably seen plots like this where it shows the cone density in thousands of cones per square millimeter on the retina as a function of eccentricity, meaning the distance from the point of fixation. There's 0 is the point of fixation, and you can see the x-axis is how it drops off. It is the distance from that fixation. And you'll often see this and people say, oh my gosh, look at how quickly that goes down with eccentricity. The resolution, peripheral acuity is just awful. But if you pause and think about it for a minute, density is actually the wrong measure here, right? For most tasks, that's not the relevant number. So density is like how many of these cones representing with these blue dots appear in this square millimeter. But for most tasks, what you want to know is the acuity, and the acuity is really how far apart do I have to make two lines for you to tell that it's two lines and not one, right? And as you can probably tell just by looking at this picture here, acuity is not about density. Acuity is about the spacing between cones in one of the dimensions. And the spacing goes as 1 over the square root of the density. So we can now take the data here and plot that cone spacing 1 over the square root of the density. And you can see that this looks much less scary. And in fact, I don't know how to scale the y-axis relative to the x-axis. So here I've made it the same scaling in both cases, and you can barely, it looks flat, right? And I've blown up a little patch so that you can see that, in fact, acuity does get worse with eccentricity approximately linearly over a wide range. But it's a much more modest effect than the cone density plot would have led you to believe. Okay. Okay, second myth is that color vision is you just basically cannot see color in the periphery. And in fact, the particularly fun version of this myth is that people are just making it up. You know that that's grass, so you see it as green. You're imagining it, right? But this also essentially comes from misreading the plot. Here's just another version of this plot. Because they're plotting density and it drops so quickly, it's hard to scale the y-axis so that it doesn't look like it just goes to 0 at the bottom. But in fact, if you blow that up, even at its lowest level, you have something like 4,000 cones per square millimeter, which is, not nothing. And in fact, color perception turns out to be pretty good, at least out to 50 degrees, which is basically where it's been measured in this particular way, so long as the patches are big enough. So this graph now shows you as a function of eccentricity, the red, blue, and green lines show you the size of the patch you need for the color vision to be approximately as good as it is for modestly sized patch in the fovea. Okay. And we know, by the way, that people are not just guessing the colors because people run good experiments where you can't possibly just guess what color the patch is, right? Okay. So let's give you more of a sense of what is true about resolution. The loss of resolution is fairly modest. The left there is the original image. Is it at all possible to make it darker in here? Anyway, so the left is the original image with the fixation at the center. The right, you'll notice, is a little bit blurry. I want to be clear, I'm not implying that peripheral vision is blurry, but it's been blurred to mimic the loss of resolution in the periphery. Okay, and I think you'll agree that if this was the loss of resolution in the periphery, you could do an awful lot of tasks without moving your eyes, right? To put this another way, if this were the information available, then the fixation might not tell you much about what people are processing, because they could be processing anything, the whole darn image they could be seeing. Okay, and I can blow up a patch here just so that you can see the loss of resolution is not nothing. So it's not a trivial effect. But this visualization is also an exaggeration. This uses, there's a guy named Stuart Anstis who has a cute Photoshop trick for mimicking the loss of resolution in the periphery, but you can't crank it down any more than this. So this is actually about 4 times the loss of acuity as actually happens in human vision. Okay. And here's just another patch. Now, just don't go to sleep. Here's another fixation just to show you the difference, and there's not much difference as you move your eyes around. So if we're all about acuity, then I mean this is a step of about 5 degrees, but in the 2 modeled fixations here, we would rarely need to make eye movements if this was the only loss of information. But it does turn out peripheral vision has significant losses of information that are important and much bigger. And this is the main issue is actually not loss of acuity in color vision, but it's what's known as visual crowding. And basically the story here is that peripheral vision degrades significantly in the presence of clutter. And this is traditionally studied in letter arrays like what we see here. If you fixate the top plus there, you should find it relatively easy to tell what the letter is off to the left when it's isolated. If I flank that letter with additional clutter, these additional letters, it gets quite a bit harder to see that central letter. If I move those flankers farther away, then at some critical spacing, it becomes easy again to read that central letter. And you might introspect also on sort of the experience that you have here. People report that they see letters, but they aren't sure what order they're in. So they're not sure which one is in the center. They report seeing letters that are kind of made up of a jumble of features from multiple letters. So there's this general kind of jumbling percept that people get in the periphery, where you can sort of tell that there are high resolution sharp lines, but you're not sure where the features are. That's a lot of the report, okay? And importantly, this doesn't just happen with letter arrays, it happens anytime there's clutter. So here's another demonstration. If we fixate that star and try to see the path of the brown subway line off to the right, and I think you'll agree that it's quite difficult. Then keep fixating the star, and I'm going to remove the clutter, okay? And I think you'll agree that now it's a lot easier. And in fact, you can see those little dashes on the line, right? So this is not a loss of acuity that's causing it to be hard, it's just the clutter, okay? And as you might imagine, our visual world is quite cluttered and complex. Crowding is going to mess up a lot of visual tasks. And if we can figure out what's going on, then we can potentially understand a wide range of visual phenomena. Now, that said, one of the tricky things about getting a handle on crowding is that there's not really simple rules about when crowding happens and when things are easier to see. So it tends to be very stimulus specific. For instance, here's two examples on the left are harder. It's harder to identify the central item. And on the right, it's easier. And it's easier because the central item has more unique features compared to its flankers. It's a very different scale. It's a very different orientation or color and so on. So the grouping or the saliency of the item you're trying to identify affects how easy it is to see in the periphery. It also just hugely depends on complexity. If you fixate the center now, you'll have a much easier time recognizing the O than seeing the details of the house, even though you can probably tell it's a house when this isolated thing is off on the side. So this all makes things very complicated, but the good news is that we have a model. We've spent basically the last decade and a half developing a model of peripheral crowding, which we call the texture tiling model. And basically it says that for a given fixation, the visual system has pooling regions, like these ellipses shown here, that get bigger in a linear way with eccentricity. They get bigger fairly quickly. And within each of these pooling regions, the visual system encodes the image using a rich set of summary image statistics. And there's lots of different kinds of statistics, but a lot of them are these sort of pairwise correlations that ask things like, if you've got horizontal stuff, does there tend to be vertical stuff nearby? Okay. And we call this the texture tiling model because what it essentially says is that peripheral vision kind of perversely seems to treat its inputs as if they're texture, even when they're not. Because it's representing them, it's encoding them in the way you would for texture, okay? Okay, so like I say, our group has been testing and improving this model for about the last decade and a half. We've gathered a lot of empirical evidence that this does a good job of explaining what happens in peripheral crowding. Tested at this point on over 70 different tasks, which is a lot for human vision. I know that's not clear how to compare that to computer vision. And we're confident enough about it at this point that we feel like we can get insights using the model for tasks that it hasn't actually been tested on. And I'm going to be doing a lot of that today. I'm going to be showing you demos of what this model says, even though we haven't tested it on those tasks. Okay. And in particular, the cool thing about this model is it lets you make visualizations of the information that's available at a glance. So you can take this original image and a fixation, lay down these pooling regions, and you can synthesize using texture synthesis techniques, new images that have the same local summary statistics, but are otherwise random. And for each combination of input and fixation, you can actually generate a bunch of these. I'll just be showing you one at a time here. And by looking at these images, we can get a sense of what information is encoded in those statistics. So for instance, here, that little inset is the original image. Here's two of the results of having a fixation at the center. And basically the way you read these is that information that's consistently available in these images is information that the model says is easily available at a glance if you're fixating at the modeled fixation, and vice versa. So stuff that's not easily available is stuff that will lead to tasks that'll be hard to do. So you can tell that from both of these, it's suggesting there's plenty of information to tell that this is a street scene, that it's probably a bus stop. You might be able to tell that that's where the name of the bus stop is, but you'd have a hard time without moving your eyes reading the name of the bus stop. You can similarly tell that there's cars on the road, but you'd be hard pressed to tell me the details of what kind of cars and maybe even how many of them. On the other hand, like it looks you have great information about that building because it's kind of textury, and similarly for the trees, like they look great. There's plenty of information to recognize textures off in the periphery in many cases. And so the general gist is that in many cases, when you're fixating the center of the scene, you can perceive a lot according to the model. You can certainly get kind of like the gist of the scene and know a lot about it at a glance. But on the other hand, in many cases, you lack details that might mean that you have to move your eyes to do a task. Okay. Now, of course, without a model, you could fixate and try to introspect on what information is available to you. And I encourage you to try that on some of the examples that I show you, but this often takes some practice. And so it can be helpful to have the model give us some idea of what the model says is available in the periphery. Okay. All right. So let's take a look at this. So again, the inset is the original image. And here's two different fixations on that scene. And the first thing to notice is that because of crowding, where you fixate matters more than it did when the only loss of information was a loss of acuity. So here, if you fixate the sign as shown on the, it'd be nice if I had a cursor here, hold on. Okay, do you see there's a little red X on the street light sign there? I don't know how to get a cursor on there. If you fixate there, I mean, a lot of the same information is available as if you fixate on the pedestrian, which is shown on the right. But for instance, there's another pedestrian far to the left, and that's easier to see if you fixate on the pedestrian than it is if you fixate on the sign. Similarly, if you fixate on the pedestrian, you get a sense of the upcoming traffic lights, according to the model, better than you do if you're fixating on the sign. But on the flip side, there's a bicyclist off to the right. And if you fixate on the sign, it suggests you might be more likely to notice that you have to pay attention to that bicyclist and not hit that person, okay? So there are a fair number of things that you get regardless of either of these two fixations. By the way, they're about 3 degrees apart in this thing here, okay? But there's also some details that you get from one fixation better than from the other fixation, okay? And you'll note that if you were really only processing where you were pointing your eyes, this would be life or death for the pedestrian, right? You're fixating the sign, you would not notice the pedestrian. You're fixating the pedestrian, you would notice him. But this says essentially that you can see the pedestrian fine with either fixation. You're going to be capable of avoiding him. Okay. All right. Okay, so some of what that suggests is that the model is saying that the information is for many tasks is available outside the fixation. And so the next question you should probably have is, do humans actually use this information, or do people really, even though there's all this information available, do they just point their eyes at the interesting bits? We should go back to that. And I'm going to show you a bunch of examples and give you some sense of when people do in fact use this peripheral information instead of pointing their eyes at stuff. But I think first it's worth thinking a little bit about why. Why is it that people use this peripheral information instead of making a saccade? And peripheral information, I'm suggesting, is weird, it's jumbled, it's imperfect in all sorts of ways, but it's also very quickly available across a wide field of view. So in many cases, if you want efficient processing, peripheral vision is what you hope to rely on. And on the flip side, there's often costs of different kinds to gathering information by moving your eyes. Those costs just come in terms of the time it takes to do that. Similarly, if you look at one location, that's at the expense of some other location. So that's another reason that you might not want to move your eyes. And I'll also talk about some examples where it adds to your memory load if you try to do the task doing multiple saccades instead of using your peripheral vision. Okay. And so what seems to be true, and again, I'll show you examples, is that human vision makes a lot of trade-offs. of the quality of the peripheral information that's available versus the cost of making eye movements. And these trade-offs also depend on a lot of things like expertise and age and stuff like that. The more expert you are, the more likely you are to use peripheral vision for a lot of tasks. Okay. So when do humans use peripheral vision? I already gave you hints that if you just want a general idea of what's going on in the scene or a big display, then you often use peripheral vision for that. We know that. Another place where we know a lot about human use of peripheral vision is for search. If you're looking at a complex scene like this one and you're trying to find the book, there's an X on the image on the right, it's sort of slightly to the right of the scene. That's your fixation. You can tell at a glance, actually, that white object there is probably a book. And in fact, you may even sort of recognize the publisher. A lot of computer science books are that publisher. And you can do that with peripheral vision. And if you can find things using peripheral vision, that makes search a whole lot more efficient. So for search tasks where that information is available, that's much better. And we know we have a lot of data that humans do use peripheral vision for most search tasks. Okay. Another place where people make a lot of use of peripheral vision is a case where you are, yes, pointing your eyes at the thing that you're actually most interested in, but because it's a big object, you actually are using a substantial amount of peripheral vision to see that object fairly well at a glance. So here we have both a bear and a cat, and the fixation shown on the right with the model. And you can see that in many cases, you look at the middle of some big object, big in terms of filling your field of view, you can actually see it pretty darn well at a glance. And that's, again, the benefits of peripheral vision giving you the right information, okay? And a particular example that we make use of a lot is seeing faces at a glance. We often look at other people's faces from close enough that they fill a lot of the visual field. And it's important to be able to judge people's facial expressions, for instance. And the model says essentially that if you fixate between the eyes, which is a common place for people to fixate when they look at each other's faces, you can basically see her whole face. You can at a glance get a sense of the facial expression. And this can be really important, actually, because if you have to move your eyes from that person's eyes to their mouth to check what the full facial expression is, that in the meantime, they might do a subtle shift of expression and that you'll miss because you're during the eye movement. And this brings up the second main reason why you would like to use peripheral vision as much as possible during tasks, which is that a lot of tasks are time critical. So driving, for instance, because things happen so quickly, you'd like as much as possible to use peripheral vision and not move your eyes. And one place we know where people do this is lane keeping. You stay in your lane. Most people fixate when they're driving on essentially the car in front of them or the curve up ahead. Here we should see the model. If you're fixating the horse ahead of you in this image, you can see those lane markers nice and clear in the road, even though you're not looking anywhere near them. And similarly, people use peripheral vision to detect hazards. We know they can do that. They will avoid pedestrians with either, in some cases, no fixations or a very quick glance at the pedestrian, maybe just to see if they're looking at you, and do the rest of it with peripheral vision. And it's worth saying a little bit about how we know for some of these examples. People monitor fixations during normal action, and you can tell, for instance, that people never look at the lane markers, and yet they're clearly using them. So they must be using peripheral vision for that. In the case of hazard detection, you can often see that people react by doing something like steering or hitting the brake before they make an eye movement to the hazard, which again suggests that you're using peripheral vision for this. And people also sometimes will block peripheral information, like they'll block those lane markers, and then people have a much harder time staying in the road. So even when you saccade, you can see them. Not being able to see them in peripheral vision makes it a lot harder. Okay. All right. So time critical tasks also brings up sports, another place where people make heavy use of peripheral vision. Sports, again, happen so fast that you can often miss information during a saccade, because as you probably know, you're almost blind during a saccade. You don't get much information then. And sports is just full of information of these trade-offs, where if you look at the ball, for instance, then you can't see the people very well. And this is why professionals rarely look at the ball. In this particular image, you can actually get a pretty good sense of what people are doing because you can see their feet really well, but it's still perhaps not the best idea. Whereas if you look at this sort of unintuitive place of the other player's shoulder, you can actually see the other players just fine. And given that you know there is a ball, you can even kind of infer where the ball is using your peripheral vision. So that may actually be the better fixation. And by the way, in sports also, there's these social costs to looking at things because you don't want to signal to the other player where you're about to go. And so you also, you're kind of tricking the other player, and therefore you don't want to make saccades for that reason as well. And so one of our colleagues, Christian Fodder, has a really nice review paper. I'll put up the citation at the end, looking at a whole bunch of different sports and seeing to what extent we can see how people use their peripheral vision versus making saccades in these sports. And he's identified essentially 3 strategies. One is this foveal spot strategy, which is the you look at the interesting bits strategy. You don't use that for many sports. It tends to be things where, like archery, where really like all the information is at that one point. And so you go ahead and look at it. That's not to say you're not seeing things in the rest of the world, but you're predominantly processing the thing where you're pointing your eyes. And then there's 2 different examples where people look between the interesting bits of information. The first is known as the visual pivot strategy, where you're planning to make a saccade, but you don't know if you're going to have to saccade to the left or the right. And so you're fixating between them so you can sort of optimally make a quick saccade whichever direction once you realize which direction is the right one, okay? And the other is, he calls the gaze anchor, where there's just not time to make a saccade. And so you've got to make do with your peripheral vision as much as you can. So you fixate between the volleyball and the player and see as much as you can with that imperfect peripheral vision. All right. So you're kind of getting this balance of information in that case. And another really simple example where you do this kind of balancing strategy is just with walking. So when you're walking, it's important to see both what's happening ahead of you, like people who might be coming towards you and stuff like that, and also to see where to place your feet. And so you can see here on the left, I've put the fixation down near your feet. And the problem with that is that then you can't see what's ahead very well. You wouldn't necessarily be able to tell much about the people that are coming or what buildings are up ahead. You can't identify them and so on. Whereas if you fixate on the right at the people that are ahead, you'll notice that at least with this sort of simple road you're walking on, not only can you see ahead now, but you can also see between your feet quite well. So that actually is the more optimal strategy. And for walking environments like this is actually what people do. People look up higher, and yet we know they're using their peripheral vision to see their feet, because if you put on these funky glasses so that you block their feet, they do a lot worse at picking their steps. They go slower and they look down at the ground more so that they can see where their feet placement is going to be. With more challenging walking environments where there's rocks and it's more uncertain and so on, people look a lot closer to their feet and weigh that as opposed to the path ahead and so on. And the flip side, of course, is that there's like trees you have to avoid that people will weigh looking a little bit more than looking down. Okay. Oh, and I just want to also point out, you'll notice that in both of these fixations, you could get a lot of information about those 2 people that you might be about to walk between, right? The kind of clear path ahead of you. And so I think another thing that you use peripheral vision for a lot is sort of like the placement of your body relative to other objects in the scene for doing things like obstacle avoidance and possibly also in some cases grasping and things like that. And that leads to somewhat more speculative things that use peripheral vision for, which are these comparison tasks. So for instance, if you're looking at those 2 dogs and you're trying to decide, are they the same? You're making sort of a symmetry judgment, or maybe you're trying to say which of those 2 dogs is bigger or something like that. Then I think you probably use peripheral vision for a lot of those tasks, but this is much less well studied. And the reason is that if you do it with a saccade, then you look at one dog and you get all the details of that one dog, and then you have to remember the details of that dog while you look at the other dog, and that's like a lot of load on your memory. So to the extent that you can do the task using peripheral vision to do the comparison instead, it's probably a lot easier and less tiring and so on. Another place where it's less speculative, though, is we do know that people use peripheral vision to judge the gaze of another person. So here, I'm not showing the fixation on the model because I want you to be able to see his face, but I put the fixation basically between his nose, on the tip of his nose there. And you can see that even though the model says, even though you might not know that for sure that's a Frisbee that he's looking at, you're pretty darn sure that he's looking at that green thing. And we know that humans use peripheral vision to do this because in the wild, after they saccade to the guy's head, they very frequently saccade to the thing he's looking at. So they clearly are judging that with peripheral vision. Okay. Now, of course, the fixation can be the focus of what people are processing. I mentioned archery already, cases where there's important information largely in this one location. There's also cases where you really need very detailed information and it's just not available in the periphery. So in the case of reading, you really have to move your eyes and you really are reading the parts that you're pointing your eyes at. Okay. So one last thing to note is that the model is showing you the information that could be available to the observer, but there's other things I haven't talked about that can reduce the information that's available. You could be distracted, you could be thinking about something else, you could be doing some problem in your head or something. That might reduce the information that you have available, even though in theory you could get that information. And these are certainly important factors, but it's also worth noting that their importance has probably been overestimated. People worry more about distraction than they probably should. And there's also this other thing, which is that they might be processing that information, but they might not be aware of it. So that also, like, there's things that they'll consciously know, and there's things that they don't consciously know, but like, they'll duck to avoid a tree branch, even though they're not aware of the tree branch and stuff like that. Okay. So in summary, what did the observer see? If you want to know this, it's important to know about peripheral vision. People often process information that's not at the fixation, especially when information is distributed across space or the situation, the task is time critical. And it may in many cases be easier to use peripheral information, even though it's imperfect, than it is to remember what happened on the previous fixation. So from the point of view of gaze estimation, this is sort of good news, bad news, right? Figuring out what people see and what they know about a situation is a super interesting problem, but in many cases, there's not a straightforward solution. On the other hand, you could say some of what this says is that your eye tracking may not have to be super accurate. Like if you really thought they were only processing the thing they were pointing their eyes at, then you really need super high accuracy. Maybe not so in this case. You can get a pretty good estimates of what information is available without having that kind of accuracy. Hopefully it helps that peripheral vision is now better understood. We've got this model that you can run. And the model peripheral vision gives you essentially an upper bound on the information that's available to the observer. And then I'll just leave you with 3 papers that I've made heavy use of during this talk. The first is a review of peripheral vision from sort of just a human vision point of view. The second one is from our colleagues, Christian Butter and others, looking at sports vision and reviewing the literature to say, what do we know about where people look and how they're processing information. And the last one is a more recent review paper we've done on peripheral vision in walking and driving, aviation. I forget if there's other applications in there, but other applications like that. And thanks to many students whose work went into a lot of this here, but especially the ones I've listed here who helped out with many of the demonstrations for the slides. And thank you.
Thank you for the inspiring talk. Okay, any question? Okay.
Is there any study on the effect of what exactly the first vision is on peripheral vision? I can imagine if it's something very bright, that you can't see things that are dark in peripheral vision very well.
So there's I'm not sure, I'm not 100% sure that I'm getting the right version of your question. So could you ask it again just to make sure?
So you were showing like this crowding in the peripheral vision.
Yeah.
That the amount of information that you can get.
Yeah.
Is there also an effect of what exactly you are looking at with your data on this peripheral vision?
I see. So is what you're pointing your eyes at affecting what goes on with peripheral vision? There are some hints of that, but the literature is not very clear at this point. There's some hints that, like, for instance, if you have a task and sort of the answer you would get from the fovea is different from the answer you get from the periphery, that has kind of an effect. So people have found sort of like conflict kinds of things. I don't know of anything where, like contrast at the phobia affects peripheral vision, but it's an interesting question. I can't think of any studies on that. Other questions?
Are there any studies on properties of the temporal space for the model? For example, what kind of properties or attributes does the object need to have for us to register it moving in the bridge?
Yeah. So there's two sets of things. One is people have just done a lot of stuff on not crowding, but just like an isolated object. What's the motion perception capabilities of peripheral vision? And so there's lots of stuff on that. There's a Hans Strasberger review that has really gory details on that if you're interested in that. In terms of crowding, there's much less understanding of what the spatiotemporal version of the model would be. But a lot of the story from the spatial domain seems to carry over to the temporal domain. So the same kind of stuff where if it's a noticeably different motion than the surrounding motion, then you see it a lot better, that kind of thing. But that's one of the really exciting future things, is to turn this into a spatiotemporal version of the model. We have hints, but there's very few studies on that. Someone over here had a question, I think.
I did, but it was basically.
Okay.
Okay, then let's thank to the Ruth. Yeah.
Thank you.
Okay, thank you very much, Ruth. Thank you, Errol. Those were some fantastic talks. Our next segment is going to be the spotlight talks from invited papers from the main conference. So I'm incredibly happy and pleased that we could invite 6 whole papers from the main conference. Gaze is certainly an interesting topic for us all. It's going to be 3 minutes per presentation. May the 2 on-site presenters please come to the front if you're here. Yes. Okay, perfect. Okay, thank you. So if the on-site presenters could just wait at the front, if that's okay, yeah. And please give me a moment while I just quickly set up. Sorry, technical issues are always a challenge for me. Okay, so we will be having 5 papers being presented, of which 3 are pre-recorded videos. The on-site presentations, unfortunately, do not have a Q&A time. Afterwards, we're having a poster presentation, which I will explain to you in a moment. It's a bit far away, but please keep your questions for the poster time. Let's get started with the first video. But let's share my screen. Just one moment, please. All right, just very quickly, Shuchong, is everything okay? Miriam?
I can't see your screen. I only see you.
Oh, that's not the intention. All right. Apologies, just a moment.
No problem.
Sorry about that, online attendees.
So just quick, this you might, so after this session, we will have poster session in the West 4A. So if the poster number will be 212-2222. So if you have poster, And after the session, please go downstairs to put your number there. And also the attendees for this workshop, please go to check the poster and have a Q&A session from there. And also we have voting the paper ready. So if you help us to find the best poster, then it's going to be helpful for us to select the best poster or one.
And just as a reminder, the poster IDs and the paper names are also on our website at gazeworkshop.github.io. Okay, Xuchong, does it look good?
Yeah, I see it. Yeah.
Perfect. We'll get started. Sorry for the delay.
Hi, I'm the director of University of Science and Technology. I'm glad to introduce our recent work on IP detection. In this work, we study a new task for multi-person IP detection in the web for untraceability. Compared with the existing work that focus on single-person scenarios, the proposed task is more realistic and have a broader application value. For example, detecting long-term IP behaviors at multi-instance level can be used to analyze attendees' attention level and emotional state change during social interactions or group activities. To support this new research task, we construct a new benchmark and link. We choose to collect data from a diverse set of unconstrained movies to meet the multi-person, unconstrained, and untrimmed characteristics. Due to the high divergence of the selected movie data source, the capture samples are also more realistic and of great challenges for effectively detecting IPs. For instance, the pose, illumination condition, and face size also differ a lot even within the same person, same video. Moreover, because of the various type of interaction among instances, there may exist severe occlusion for people in and out scenarios, making it harder for both instance organization to do IP detection. To perform IP detection, previous methods generally take a sequential approach containing face detection, face tracking, landmark detection, and classification of the pre-extracted local occlusions within a rigid temporal window. Such a sequential approach is hard to meet the real-time running requirements under multi-person scenarios, and usually obtains an inferior performance due to unreliable local occlusions under unconstrained cases. In this work, we present InstBlink, a one-stage multi-person IP detection framework that can simultaneously detect human faces, track them along time, and do IP detection at instance level. Specifically, inspired by the recent query-based methods, we use spatial temporal queries to store the face and IP features of each instance within the entire video clip. Applying different tags, shared query features can allow us to achieve face detection, face tracking, and instance level IP detection at the same time. Under this framework, features from some tasks can be effectively shaped and interactive to obtain a superior performance with higher running speed. Here we show some prediction results from InstBlink. Our method aware the attendees robustly and detects IPs under different visual groups and head pose. For more details, please refer to our paper in the project page. Thank you for your time.
Hi everyone, our work is thought. Hi everyone, our work is thought-free adaptive gaze estimation by uncertainty reduction. The authors are Xin Jiabei, Shiguang, and Xilin from Institute of Computing Technology, Chinese Academy of Sciences. The gaze estimator's performance often decreases when they are trained and tested on different domains. The training data are usually collected under controlled conditions, which is convenient to measure and compute the true gaze vector. But the trained estimators are used in diverse and uncontrolled environments. In our work, we aim to improve the gaze estimator's performance on target data. However, due to the privacy and efficiency concerns, it's difficult to access the source data and target data at the same time. As a solution, we first train the model with labeled source data. Then, we adapt the source trained model to the unlabeled target data. The adapted gaze estimator is used to predict the text image. The source-free adaptation is based on our observations about the relationship between domain gap and uncertainty. We discovered a larger domain gap between the target and source leads to a larger model's uncertainty. The uncertainty can be decreased if we enhance the quality of the image and reduce the domain differences. Under the cross-domain protocol, the gaze error increases as the uncertainty grows. Therefore, we propose to reduce gaze error by reducing both sample and model uncertainty. Sample uncertainty is mitigated by enhancing image quality. Model uncertainty is reduced by minimizing the prediction variance. The detailed framework consists of 3 steps. First, we collaboratively train a phase enhancer and gaze estimators on source data. We keep a set of gaze estimators at different iterations during the training. Then, we cannot access the source data. We freeze the phase enhancer and update the gaze estimators in an unsupervised way by minimizing the model uncertainty and maintaining the gaze estimation ability using pseudo labels. Finally, we predict the gaze using the phase enhancer and the mean estimator. We conducted experiments on cross-domain gaze estimation using 4 datasets. 2 of them are used as the source and 2 are target. The experiment's results show our method outperforms others on these cross-domain gaze estimation tasks. The visualized examples show that phase enhancement can improve image quality, reduce gaze errors, and model uncertainty. Thanks for your attention.
So good afternoon. Good morning, everyone. So my name is Zhu, and today we will present our work titled Latent-to-Latent Translation for Gaze and Head Redirection. So our target is modifying the gaze directions and head orientations on the for high resolution full face images without affecting other facial attributes, given the provided directional vectors as the conditions. So our approach involves editing the target facial attributes in the latent space using a conditional gain pipeline. So given the provided target condition CT, we can transform the encoded latent vectors FS into FT hat, and then it can be fed into the generator for image synthesis with edited attributes. So to achieve conditional redirection in the latent space without affecting other facial attributes or identity information, we only project the target facial attribute relating features into a embedding space Z to achieve transformation in an interpretable manner. So we use a with-sharing D projector to transform the embeddings back to the original latent space for original attribute removal and new attribute addition. So to achieve gaze and head redirection on high resolution full face images, we combine the redirection trans with the gain inversion pipeline, named as redirection transgain. So we utilize E4E as the image encoder and StyleGAN as generator. So during the training of this end-to-end pipeline, we freeze the parameters of the encoder and generator to make sure that the editing is implemented in the original latent space. So given the 18 layers of latent vectors in double+ space, so we introduce layer-wise editing modules for gaze and head redirection. So redirection transgain can adaptively estimate the weights based on arrows between the estimate results and between the inverted results and estimate labels from the latent vectors. So this allows us to determine which layer should contribute more to the desired facial attributes editing. So let's now examine the evaluation results within datasets and cross datasets, comparing redirection trans with state-of-the-art methods. So we evaluated the performance from the gaze and head redirection accuracy, gaze redirection induced arrow to head, and head redirection arrows induced arrow to gaze, and also LPIPs. So here are the qualitative results from redirection transgain, so which successfully achieves gaze and head redirection in high resolution images. So we can observe that the redirection transgain is able to redirect the gaze directions and head orientations while maintaining other facial attributes. So our proposed redirection transgain can also correct the gaze as a compensation for the gain inversion pipeline. It's kind of like a subtask for the gain inversion task by using the same image as both input and target images. So we ensure that the inverted image maintains the original gaze directions, even without explicit gaze direction labels for the input image. So this demonstrates the effectiveness of our proposed method in the gaze correction task. So thank you for listening.
Good morning, everyone. I'm Xiangwei Shi from Delft University of Technology. I'm very happy to be here to present our work gaze nerve 3D aware gaze redirection with neural radiance fields. It's a joint work of TU Delft, ETH Zurich, NVIDIA, and University of Birmingham. First, our work focuses on the gaze redirection task. Given a face image and its corresponding gaze label, the task is to generate synthetic face images with different target gaze labels. Existing methods for gaze redirection tasks can be mainly categorized into image warping and synthesizing new images with deep generative models. However, they both have drawbacks. Image warping method now model large change due to its inability to generate new pixels. Well, 2D generative models can produce high-quality face images and allow for large change of gaze direction. They do not take the 3D nature of this task into consideration. Recently, a nerve-based model of head nerve was proposed to generate face images with efficient control of face attributes. So in our work, we propose gaze nerve. It reformulates this task as 3D neural volume rendering, and it disentangles the face and eye regions, allowing for the rigid transformation. Given the target gaze label and the latent codes related to the facial attributes and the 3D locations as the input, gaze nerve employs a novel two-stream MLP structure to learn the features of eye region showing in yellow and the features of face-only region showing blue. We explicitly apply a 3D rotation matrix on the features of two eyes, and then combine the features from two streams to shown in orange to render the whole face. And then we feed three features into the same neural rendering module to generate the final 2D images. For the experiment, we show that gaze nerve achieved the best performance on gaze and head pose redirection error, and also the comparable performance on the image quality compared to the state-of-the-art methods. We also visually compared the generated images with the ones by the two previous state-of-the-art methods, STAD and head nerve. The blue circled images are generated by the STAD. They show that STAD suffers from the loss of personal identity information. And the red circled images are generated by head nerve, even though head nerve can preserve the personal identity. But they cannot generate fine-grained eyes. And also in some cases, it shifted the gaze direction. Compared to the two previous state-of-the-art methods, our work gaze nerve can generate the high-quality face images with target gaze direction and fine-grained eyes. Here are some animations. They are generated by gaze nerve with three different settings: changing the gaze label only, changing the head pose only, and changing the gaze and head pose at the same time. Thank you. Please check our paper for details if you are interested.
Hi, I'm Hu Zhenxi. I'm going to present you our research, Cvpr, the dataset and baseline for gaze following from 2D to 3D in indoor environments. Gaze following requires inferring where the person in a sense is looking. However, a summary of datasets used for gaze following tasks reveals defects in the way they collect the gaze point labels. So, we first present two key problems. To address the problems mentioned above, we developed a system to record gaze behavior and released the novel GFIE dataset with reliable annotations. We also propose the baseline method for improving gaze following. Some test samples on the GFRE dataset are given for an overview. First, we stated the motivation for this study. We conducted a survey of datasets used for gaze following and found defects in the way they collect gaze point labels. Most datasets are manually annotated, but the subjectivity of annotators may cause annotations to deviate from the actual gaze target. In addition, label intensity is another drawback. The eye tracking device can capture annotations automatically and alter subject's appearance in the dataset. It may bring the gap with the gaze-related behavior in the nature environment. In this work, we proposed a novel system for establishing our GFRE dataset. We use the laser spot emitted by the laser rangefinder to guide and locate the gaze target. After collecting various gaze behavior, accurate annotation can be provided for establishing GFRE datasets. In addition, we introduced a stereo field of view in the proposed baseline method for improving gaze following. These are our main contributions. Next, we briefly describe the workflow for GFRE dataset generation. The gaze data collection system consists of a laser rangefinder and an RGBD camera, Author Kinect. Author Kinect is set to capture RGB and DIPS images. Laser rangefinder are used to measure distance while emitting laser light. Then we can operate the laser rangefinder to guide the subject's attention target through the laser spot. The subject is always staring at the laser spot while performing in front of the camera. After collecting various gaze data, we needed to build a workflow to generate the GFRE dataset. There are 3 key steps here, including laser spot detection, laser spot elimination, and annotations generation. We first propose the Cvpr algorithm for laser spot detection. Then we use the existing image impacting algorithm to eliminating laser spots. Our GFRE dataset provide annotations, including head bounding box, eye locations, and gaze targets. The first 2 are generated by detectors, where the gaze target can be obtained based on the detected laser spots, camera intrinsics, and mirror distance. Failure case in annotations were manually checked and corrected. These 2 demos are examples of laser spot detection and eliminating laser spots. In the video on the left, the detected laser spots are in the red bounding box. The GFRE is a multimodal dataset. It consists of over 70,000 frames and contains various gaze behavior of 61 subjects. The dataset split are shown in the table. Statistics from 2D plane to 3D space are also shown in the figure. Some things in the GFRE dataset are displayed here. We also propose the GFRE baseline model. It consists of 3 key components. One module is used to estimate gaze direction. Based on predicted gaze direction, the module that perceives the stereo field of view is proposed to highlight regions that a person pay attention to in space. Then we can infer gaze targets based on the module for generating gaze heat map. A strategy for 3D gaze following is also designed to extend the proposed wisdom.
Okay, I'm sorry, but I think I'm going to interrupt the video here because for fairness as well, the other talks were 3 minutes long. Firstly, thank you very much to everyone for presenting for the main papers, that is. Of course, there's Cvpr main conference papers, so you will be able to visit them again at the upcoming poster sessions, which I highly recommend that you do. The poster session will begin soon. I recommend that the non-presenters get a cup of coffee and take it easy and head down slowly towards the poster session. It is a long walk, so please take your time. Poster presenters, might be a good idea to hurry up, but please come to the front and then I'll try to help you guys along towards the poster session. Please note that we have to pick up our posters and hang them, so really take your time, the rest of you. And yeah, have lots of coffee in it. See you guys later at the poster session and back here at, I think, 11.
I think we need to.
I guess it's better to take the laptop, right? It's not that safe here. Okay.
Me too.
Thank you.
Thank you.
Oh, yes, thank you. I was going to ask about it.